This lecture is going to be on mid-latitude cyclones, which I'll refer to as MLCs. We'll look at the formation of, the evolution of, and how mid-latitude cyclones affect our local weather. So know that mid-latitude cyclones are responsible for local weather patterns, including extreme and severe weather. You should be able to identify the stages of evolution of a mid-latitude cyclone and understand the changing conditions as an MLC moves through an area. And we'll talk about this in terms of denoted by a transect. And here there's two transects on this map. So notice that the characteristic comma shape or apostrophe shape. So we can see this a couple different ways. So this is a characteristic, a signature look for it. So an MLC, the primary weather producer in the middle latitudes. So the life cycle. How do they live, how do they age, and how do they evolve? Well, they form along a front where air masses are moving parallel to the front in opposite directions. We'll be looking at continental polar coming from the north and maritime tropical coming from the south. These two interact, and this is where we find our mid-latitude cyclone. And the characteristics are this apostrophe shape. So I'm trying to reiterate that it has a very distinctive shape to it. So the life cycle. The frontal surface takes on a wave shape with low pressure centered at the apex of the wave, the highest point. The flow of air is counterclockwise cyclonic circulation, right? So it's still a cyclone. It's this counterclockwise motion. And that's consistent with the low pressure characteristic in the northern hemisphere. The warm front and the cold front form. These are boundaries of two conflicting air masses, both continental polar and maritime tropical. The cold front catches up to the warm front and produces an occlusion, and that's at the point of contact. The warm sector is displaced aloft, right? Warm air rises. And the pressure gradient weakens, and the fronts discontinue, and that's toward the end of it. So that's the evolutionary stages. Let me show you pictures that associate with that. So here we have this front that develops. It's point A. And this could be in kind of northwest Canada into Alaska. So it develops. And then the wave develops. And notice we get this buckle here. We get cold air and warm air that begin to kind of do their dance. Notice where the front is developing, we get two different directions of airflow, cold and warm. But then it starts to mature and starts to begin to stabilize. So letter C is where the cyclonic circulation is established. We get this very distinctive warm front and this very distinctive cold front sector. Location D. This is where your occlusion begins. Your occlusion is going to take place where you have, let's just say the warm and cold air are going to begin behaving a very specific way. Warm air is going to rise and cold air is going to be moving beneath it. Location E, we have the occlusion front that develops, and the occluded front is going to be noticeable. It'll be the tail, it'll be up here at the top. It'll be in and around the warm and the cold sectors. It'll be where they kind of, the cold air begins to push underneath the warm air. And then at F, when the storm runs its evolutionary path or its life cycle through the mid-continent of the United States, it eventually dissipates. The cyclone dissipates. The water has less heat than the land at this point to fuel the cyclone. So if we slow this down, just to make sure we reiterate this, the first three stages here at location A, the front develops in the Pacific Northwest or Southwest Canada. At location B, we get this wave developing. The circulation pattern develops around the wave. This is what we're establishing. At location C, the cyclone begins to take shape. We have very, very obvious low pressure established or generated. It's even visual and measurable. Location D, here's your occlusion. The occlusion begins is where cold air is going to underride the warm air, and the cyclone begins maturing. At this point, it would be a mature stage. And location E, the occluded front develops and the cyclone is fully formed. So we have this warm, cold front, so warm front, cold front, occluded front. And this here is going to take place, obviously the further it travels, the more it has time to mature and get this occlusion in there. And then lastly, it's going to dissipate, it's going to break down. And the breakdown commences once it reaches the Atlantic Ocean. Once again, it just doesn't have the heat energy, it doesn't have the fuel to have it continue growing and evolving. So mid-latitude cyclones move eastward across the United States. The first signs of their approach are in the western sky. So if we look to the west, we would be able to see a particular, the weather on its way. It's traveling towards us. And it generally requires 2 to 4 days to completely pass over a region. These are the largest weather contrasts that we get occur in the spring. That the largest weather contrasts where we have the coldest and the warmest air that's colliding. So changes in weather associated with the passage of a mid-latitude cyclone, it changes depends on the path of the storm. And we can draw a transect to analyze the changing conditions. And that's why the transect is important. The transect allows us to kind of slow it down and say, okay, if we're at this location, what's going to happen as this condition travels through us, or as the mid-latitude cyclone moves through. Notice that this picture, this transect here, is located up here. You get this very obvious region in the middle. That's just rain, right? We have this particular cloud sequence. And out in front, relatively clear skies, and behind, right, the clouds are going to be clearing. Particularly this, so this transect is showing you what's taking place up here. And this transect is showing you what's taking place in this picture here. So we have this warm front coming. We have this very characteristic sequence of clouds. At location C, it's going to be relatively clear, but there'll be some cumulus clouds moving in. But this is the warm sector. If you're in behind the warm front, this is your warm maritime tropical air. And then we have our severe potential, the storm at point D, and then location E is going to be behind or within the cold front itself. So this transect associates to this picture. This transect is associated with this picture. So the idealized weather, the changes in weather associated with the passage of a mid-latitude cyclone. So weather associated with the fronts, the warm front, clouds become lower and thicker. There's light to moderate precipitation. And after the passage of the warm front, the winds become more southerly and temperatures warm. They increase, right? If warm air is moving in, the southerly breeze and the warmer temperatures should make sense. So the weather changes associated with the passage of a mid-latitude cyclone when we look at a cold front. We'll get a wall of dark clouds. We should get heavy precipitation, potential hail, and occasional tornadoes, right? This is if severe weather, if it has the ingredients for severe weather. Yet after the passage of the cold front, the winds become more northerly, skies clear, and temperatures drop, right? We've got this cold air moving into warmer air. So this is the characteristics that take place, the sequence, after the cold front moves through. So the cloud patterns typically associated with mature mid-latitude cyclones. When we look at a warm front, we get cirrus, we get cirrostratus, we get our nimbostratus. Our nimbostratus are going to be bringing the rain. And then we get our altostratus at the end of it, the tail end of this. That's looking at this transect here. I'm naming the clouds as to the way we see them. At this location, at this transect, as the warm front's moving through, we get our cirrus, cirrostratus, altostratus, and nimbostratus. So it's going to be raining all in around the warm front boundary. At location C, it's going to be warm. It can be clear, it can be cloudy, but this is just a cumulus cloud, those puffy cotton ball clouds. But at location D, this is where we get our cumulonimbus potential. We have cold air, warm air. We get a very clear gradient difference. A steepness of the slope is going to be significantly, noticeably different. And this has the severe weather potential. And afterwards, it's going to be very clear. We're going to have clear skies kind of prevail, because all of this is going to wring out all the moisture in the air. So clear skies commence. So here's a satellite view of a cyclone over eastern part of the eastern part of the United States. Actually, we are right in this very well developed apostrophe or comma shape that we see here. We would be kind of right behind this location here. Actually, we'd be over here a little bit. Where are we anyway? There we go, right here. And it's a distinctive comma or an apostrophe shape. I'm trying to show you this. Moving on. So the role of air aloft, this is where we need to make sure we understand that. Cyclones and anticyclones, they're generated by upper level airflow. They're also maintained by upper level airflow. So you'll hear that the jet stream is going to be influencing the air. They're typically found adjacent to one another. That with the cyclone itself, we're talking low pressure. Low pressure system, surface air converges, it's going to rise, and it's going to diverge aloft. Right? It's the outflow, the divergence aloft, that sustains the low pressure. So the role of air aloft for the anticyclone, it converges and sinks. So this subsiding air is going to be associated with high pressure. The surface winds are going to be diverging. They're going to be spreading out once it reaches the Earth's surface, obviously deflected to the right due to Coriolis. But you get convergence aloft with high pressure. It's going to sink or subside, and it's going to flow outward, which is divergence at the Earth's surface. So anticyclones typically or tend to bring in stable air in clear skies. There you have a summary of mid-latitude cyclones.